So, welcome everybody. I'm glad to see so many are taking advantage of these really very cold temperatures we've got in comparison to next week, last week. Today we've got a speaker who's local and also from Caltech, Kareem El Badry, and I'll hand over to Hans Walter to give the laudatio.
Yeah, good afternoon. It's a really great pleasure to welcome Kareem El Badry for today's colloquium. Let me briefly tell you about Kareem and also perhaps a little bit about my interactions. Kareem was an undergraduate at Yale and then a graduate student at Berkeley, where I think pretty much 10 years ago, I first met him when I was a visiting professor. Kareem at the time had started his thesis, was a couple of years into it, doing mostly cosmological simulations, galaxy formation, dense cluster formation, etc. And then made the, some would say brave, I would say inspired decision to shift field rather drastically halfway through his thesis. Kareem started working on stars, binary stars, and also away from simulations to dealing with data. Kareem actually has been a visitor to Heidelberg here for the last 10 years, I believe now. And so his career subsequently graduated from Berkeley, was then 2 years at the Harvard Society of Fellows, and for the last years has been faculty at Caltech. Kareem has really had tremendous impact across many aspects of binary star physics that he'll tell us about. I guess he had the joy of picking the nomenclature of Gaia BH1 and BH2 because that's perhaps one of the most spectacular things he's done. Over his brief career, he has already gotten a number of fellowships and awards, among them a Sloan Fellowship Award and a MacArthur Award. So we're very happy to have him back here, and he will tell us, I guess, what to believe and what not to believe about binary stars.
All right, thank you, Hans Walter. Thanks everyone for being here. All right, I think that looks good. So I'll just say at the beginning, I know some of you work on totally different fields, and some of you know a scary amount about this field, so I'll try to have it somewhere in between. If I say something that's not clear, you can raise your hand during the talk and ask a question if you want, or ask it afterward. So my background slide here is a picture of one of the brightest stars in the sky. It's called Zeta Off. Zeta Off is on here because it's the nearest O star to the sun, the nearest star that we think when it dies has a good chance of becoming a black hole. Zeta Off is what's called a runaway star. That means we think it used to be in a binary, but its companion has already died. Maybe now it's a black hole or a neutron star, and because of that, it's moving through the interstellar medium faster than the average massive star, blowing this bow shock. So Zeta Off, like I said, is the nearest O star, but there are lots of others like it in the Milky Way. There are about 20,000 of them, depending on exactly what you call an O star. They're bright. We can basically count them. And they're important for various aspects of the galaxy's evolution. They're the main source of ionizing photons and momentum in the interstellar medium. But they don't live very long. The typical lifetime of these stars is something like 5 million years. And so although there are only 20,000 in the Milky Way today, there are much more that were in the Milky Way at some time in the past and have died and now left behind black holes. And so if we wanted to estimate the total number of O stars that have ever lived in the Milky Way, we could do a calculation like this, where we take the total number that there are today and then multiply by the ratio of the age of the Milky Way to the typical age of an O star. And we get that there should be something like 4 times 10 to the 7 black holes in the Milky Way. If we count a little more carefully, if we account for the fact that the star formation rate of the galaxy is not always the same, we might get a number a little bit higher, something like 10 to the 8. But the exact number is pretty uncertain and something we'd eventually like to measure because we don't know exactly which massive stars leave behind black holes to begin with and which ones leave behind neutron stars or no remnants at all. Another thing you can get from this kind of calculation is that the nearest black hole should be something like 10 parsecs away. And we can calculate that because zeta off, the nearest O star, is something like 100 parsecs away. There should be about 1,000 black holes for every O star, and a factor of 1,000 in volume is a factor of 10 in distance. So 10 parsecs is pretty close relative to basically all other Milky Way scales. So they should be all over the place. So that's basically the point of this talk, is where are all these stellar mass black holes, and what can we learn about the population from the ones that we find. So there are a few different populations of stellar mass black holes we know about. The first, which has been studied now for about 50 years, are these X-ray binaries. There are about 20 of these for which we have an X-ray source, we have an optical companion, we can measure a radial velocity curve of that optical companion, measure the mass of the black hole, and prove that it is in fact a black hole. Here's a census of them as of 2006. There have been a few additions since then, but this population hasn't changed that much in size over the last few decades. And we've learned a ton about black holes, and especially about accretion, from studying them. In addition to those 20 or so confirmed X-ray binary black holes, there are another 50-ish X-ray transients that we think are black holes based on their X-ray properties, but are not dynamically confirmed. That is, we haven't been able to measure the mass of the compact object. And so here's a graph showing the number of known and suspected black hole X-ray binaries as a function of time. And you can see these discovered ones, that is X-ray source that we think is probably a black hole based on its X-ray behavior, is growing linearly. Basically, one or two of these is discovered every year when it goes into outburst. But the number that can be dynamically confirmed through optical follow-up has been increasing more slowly and has kind of plateaued since the early 2000s. And that's because most of these new objects that we're discovering are very faint in the optical. They're on the other side of the galaxy or deep in the disk. And so there's too much foreground extinction to be able to study them. And then finally, a newer addition to the black hole population is systems like this, which I'm calling wide black hole binaries here. Basically, here you have a black hole that's orbited by a star, and there's no significant accretion onto the black hole, so you don't see any X-rays. But you can infer that the black hole is there based on the orbit of the star, which tells you something about the mass of the companion, and then you look and you don't see another star there. Here's another way to look at the black hole population. I'm sure many of you have seen a plot like this before, but the y-axis here is stellar mass. This is the x-axis has no information. This is basically a census of all of the known compact remnants as of a few months ago, for which we have mass measurements. And so all of these blue systems up here are merging black holes discovered in gravitational waves. So just for context, before we were talking about black holes in the Milky Way, these are not in the Milky Way, they're at cosmological distances. But when they merge, they produce a very bright gravitational wave signal, bright and gravitational waves, that we can detect them all throughout the universe. And then down here, in red or magenta, we have those black hole X-ray binaries, which we talked about, as well as some of the some of the black holes in non-accreting binaries. And finally, down here, we have neutron stars with good mass measurements. Most of these are recycled radio pulsars that have accreted some mass from their companion and been spun up. And so these are basically the three best handles we have on the black hole and neutron star population. But you can see they're probing, they all have very different observational selection effects, and they're probing different populations. So one of the things that people have asked about this diagram is if you look at the masses of the confirmed neutron stars down here, they're all below about 2 solar masses. And the black holes, most of those are above about 5 solar masses. It's been proposed that there's a gap between these. And so you can see it's not really strictly a gap in that there are some objects with masses in between them, but it seems like there's at least a bimodal mass distribution where either you're likely to make a less than 2 solar mass neutron star or a more than 5 solar mass black hole. And so that might tell us something about the supernova mechanism and about the collapse of massive stars, but it's probably also driven some by observational selection effects. And so one of the things we'd like to measure is what is the mass distribution of black holes across this whole axis, black holes and neutron stars. Another thing that might jump out at you is that all of the objects that are highest in this diagram with the highest masses are the gravitational wave sources. So even before merger, many of these have masses of 30 or 50 or 100 solar masses, which is higher than the typical masses of the black holes down here that we see electromagnetically in the Milky Way. And so in some sense that's expected in that it's easier to detect gravitational waves from more massive black holes, at least up to a point. So there's kind of a bias in favor of high masses. But nevertheless, it means that we don't have direct analogs of these most massive black holes in the Milky Way. And so we'd like to understand what kinds of stars they form from and how they get to be so massive. So here's just a list of some of the open questions that we'd like to answer in this field. I talked about some of them. So what's the mass distribution, not the observed, but the intrinsic mass distribution of black holes and neutron stars? How do the mass distributions of black holes and neutron stars depend on the stars that they're formed from? So on their initial masses, on their metallicities, maybe on properties like their initial spin. What kinds of kicks are black holes born with? We think often stars die in supernova that have some asymmetric mass loss, and so that will impart what's called a natal kick on either the black hole or the neutron star, and we'd like to be able to measure that to constrain the supernova mechanism. Almost all the black holes that we can see are in binaries, and so we'd like to understand the story of how they got there, what fraction of the population do we see today in binaries, and which ones didn't make it to be binaries, either because they got unbound or because they merged. And finally, what else is out there? So this is kind of open-ended, but what we're going to be doing is using stars as dynamical probes for unseen masses. And so in principle, this lets us find anything besides the kind of stellar mass black holes we've been looking for, right? If we could find a star orbiting 1,000 solar mass black hole, or a 1 solar mass black hole, or 2 black holes in a close binary. And so if we do a survey of all the objects that stars are orbiting, we might find something new. Okay, so most of what I'm going to talk about is enabled by the Gaia mission, which I'm sure many of you are very familiar with, but I'll just give a quick summary. So Gaia, for 11 years, sat at L2 and scanned the sky. It had these 2 cameras that it rotates on its axis, and as it rotates, these cameras sweep out a ring on the sky. But then the precession axis rotates, and as a result, Gaia can eventually cover the whole sky, roughly once a month on average, although it depends where you are on the sky. And so the main goal of Gaia, each time it looks at a position on the sky, is to measure stellar positions with respect to some kind of reference frame with very high precision. And so the amazing thing about Gaia is just how precise these measurements are. So for stars at the bright end, that means typically brighter than about 13th or 14th magnitude, this precision reaches something like 100th of a milli-arc second. And so I wanted to say a little bit about what 100th of a milli-arc second is. So you can imagine I'm in California with my telescope. I point my telescope at us in Germany. The Earth is not curved. In that case, 100th of a milli-arc second is about the diameter of a human hair, as seen across the US and across the Atlantic. So incredibly precise measurements. And these are necessary because the motions of stars on the plane of the sky are incredibly small. Just another reference point of what is 100th of a milli-arc second. This here is perhaps the highest resolution image ever made in astronomy, or one of the highest resolution images. This image is 0.1 milli-arc seconds on a side. So if you have a bright star, Gaia can centroid that star in the sky to an angular scale of about 1/10 of this image. So very precise. So Gaia makes these kind of measurements all across the sky all the time. And eventually, once you can collect a lot of them, you can fit an orbit, right? You find that some stars are just moving in straight lines, but other ones are going in these little ellipses because they're orbiting another star, or in some cases, a black hole. And so here's some real Gaia data from Gaia DR3 of a basically normal binary. You can see in this was the data from DR3, which is about 3 years of observations. You have something like 30 measurements of position as a function of time. Here we've already taken out motion because of proper motion and parallax. And so from those measurements, you can measure the orbital period, you can measure the distance from parallax, you can measure the size of this ellipse, and then from Kepler's third law, you can measure the mass of the companion, as long as you can make an assumption about what the mass of your luminous star is. And so that's basically the game, is to fit these kind of orbits, and then look for cases where the companion is very massive, but is not contributing very much light. So sadly, Gaia has stopped taking data as of last year. The final observing baseline is almost 11 years. And on average, by the end of the mission, typical stars were observed something like 120 times. So fortunately, 120 is large compared to 12. 12 is the number of free parameters in an astrometric orbit for a binary. And so that means that the Gaia data are very good at constraining orbits of binaries as long as the observing baseline is less than about 10 years by end of mission, or maybe less than about 20 years. Even though there's 11 years worth of data, so far only the first 2.7 years of this were published in Gaia DR3. But the next Gaia data release is coming at the end of this year, on December 2nd, 2026, and that will have the next 2.7 years. So in total, it'll be something like 5.5 years of observations. And I'll say more in a little bit about what we can hope to find with Gaia DR4 data. Okay, so what I'm showing here is the period distribution and then the HR diagram of all the binaries that got orbital solutions in Gaia DR3. There were about 170,000 of them. And just for context here, I'm showing the binaries that had orbital solutions from the best mission before Gaia at astrometry, which was Hipparcos. So Hipparcos, by the end of its mission, produced astrometric orbits for 235 binaries, and in Gaia DR3 we got 170,000. So it's an enormous increase in sample size, and even if you don't just consider these Hipparcos orbits, but if you consider all the other ways that you can constrain binary orbits, like radial velocity surveys from the ground, it was still about a factor of 50 increase in sample size. And so that means if you want to look for rare objects, it's a good place to look. What I'm showing here is now the observational HR diagram. Just for context, this is where the sun is. And so basically most of these stars are solar type stars. They're almost all within half a solar mass and 2 solar masses. And that's basically just a function of how sensitive Gaia is. In general, astrometry is more sensitive to objects that are nearby. And low mass stars are more common than high mass stars. So you might think that it would especially detect low mass stars. But low mass stars are also fainter, and so the peak sensitivity ends up being somewhere around 1 solar mass. Okay, move this out a little bit. Okay, and so starting with this, with all these astrometric orbits, you can try to isolate cases where the companion must be a compact object. And from that, we found something like 5,000 cases where we have a solar-type star orbiting a white dwarf, something like 50 where we have a solar-type star orbiting a neutron star, and something like 5 where we have a solar-type star orbiting a black hole. And these numbers are basically the numbers you get when you start with a Gaia catalog, assuming all the orbits are accurate. And then in my group, over the last few years, we've done spectroscopic follow-up on many of these systems and tried to figure out both the completeness and the false positive rate of these orbits. And so it turns out for the white dwarfs, almost all of the orbits are correct. We understand the sample pretty well. For the neutron stars and the black holes, a smaller fraction of them were correct, and that's just because we're probing the tails of the distribution. So we're looking at a place where there are intrinsically not many objects, and so a small amount of false positives will lead to a higher contamination fraction. Okay, so I'll just walk you through some of the more exciting systems we found from this catalog. The first one is called Gaia BH1 here. So here it is on the color magnitude diagram. You can see it's basically where the sun was on the last diagram. We have a solar type star with a mass just a bit less than the sun, a metallicity pretty close to solar. When we look at the astrometry, Gaia sees the star going in a somewhat eccentric orbit on the plane of the sky with a period of about half a year. And then the parallax tells us that it's about half a kiloparsec away. And then we can confirm this astrometric orbit by measuring follow-up radial velocities from the ground, which are plotted here. And then this black line shows a joint fit to the plane of the sky motion and the radial velocities. And so when you combine those, you can measure the 3D orbit of this star through space. And then we take this mass estimate based on the spectrum and how bright it is, we can get a mass for the unseen companion, which in this case is 9.3 solar masses. So we have a star that's orbiting something else that's 10 times more massive than it is. But when we look at the spectrum, we only see light from that one star. And so we haven't detected the black hole in some sense, but we've detected there's something massive there, and we can't think of any other physical scenario to fit that much mass in that small of an area without producing any light. I'll just point out one of the nice things is that these mass estimates actually become quite precise. They have a precision of something like a few percent, at least for the nearest objects. So although so far we only have a few of these, we can measure the masses more precisely than pretty much any other method of looking at stellar mass black holes. Okay, so immediately the question we had is, how do you form a system like this? So we've got this somewhat eccentric orbit, about an AU scale, and a 9 solar mass black hole. So our first guess is, well, black holes form from massive stars. So this 9 solar mass black hole, or 10 solar mass black hole, if we look at stellar models, it should have formed from a star with an initial mass of something like 40 solar masses at solar metallicity. This is pretty uncertain, but in that ballpark. So we can then say what happens we put a 40 solar mass star there. In that case, the initial separation of the other star would have to be closer because the orbit will expand when the star loses mass. And say, let's let stellar evolution happen. Well, what happens is that near the end of its life, this 40 solar mass star will expand, and it'll become what's called a red supergiant. And red supergiants are very large. So what's shown here is the maximum radius, according to stellar models, of the progenitor of this black hole. It's several AU, so it's too big to fit the current orbit of this solar-type star inside it. And that just tells us that you must have had some kind of interaction between the progenitor of this black hole and the companion star if they formed as a primordial binary. That's not necessarily a problem in that we think probably almost any time you have a star orbiting a black hole in a close-ish orbit, you'll have had some interaction. The challenge really is that there must have been some interaction, but the orbit is still pretty wide. So typically what binary models will tell us is if you have this kind of interaction, the star will start to spiral in through the envelope of the massive star. And if it's lucky, it might liberate enough gravitational potential energy as it inspirals to eject the envelope. That's what's called a common envelope evolution. It's a little uncertain whether that can work for a case like this where you have a really extreme mass ratio. But if it could work, the outcome would be something like this, where you have now a solar-type star orbiting the helium core of this massive star, and the envelope has been ejected. The challenge, though, for getting that to work for this system is that now the star should be right above the helium core with a separation of a few times the stellar radius. But in fact, in Gaia BH1, it's hundreds of solar radii above the core of this star. And so it's been difficult to get this kind of model to work. Just I'll call that normal isolated binary evolution for the Gaia black holes. So many people in the community have proposed different models to try to solve this problem and explain how these kinds of systems form. I have a list of papers that I put up here as of a few weeks ago. I'm not totally sure if it's complete, but you can see there's a lot of papers, significantly more models than black holes so far. So I'm not going to go through every one of these, but I'll give you kind of a flavor of different ways that you might be able to make this work. So one is you can say that story I just told you, that the massive star gets large, is not actually true. Right? Maybe in some cases the star stays small, either because it's rotating really fast or because it has strong enough winds on the main sequence that it never expands, or it has strong winds that make it start to get large, but basically keep the mass loss from the massive star without it ever flowing its Roche lobe. So there have been a lot of papers exploring that possibility. Another possibility is maybe it started not as 2 stars, but as 3. So for example, maybe you have 2 massive stars in a close binary. They can interact with each other and exchange mass, and they'll both kind of truncate each other's evolution so that neither one can ever expand to become a red supergiant, and the solar-type star is safe at larger separations. Or there are other kinds of configurations you can have with triples where the third star is somewhere else. And then another possibility is that maybe the star and the black hole didn't form together in a binary at all, but maybe they were just assembled later on through dynamical evolution. And I'll talk about that in a little more detail in a minute. But that kind of evolution could happen either in low mass clusters, like the kind of clusters we see in the Milky Way today, or in more massive clusters, like the progenitors of globular clusters. Okay. In the meantime, we found a few more of these black holes. So this one, called Gaia BH2, is basically a similar story. We again have a star that's about 1 solar mass, solar metallicity, orbiting a companion that's 9 solar masses. A little bit longer orbital period now of 3.5 years, or a separation of 5 AU. And this time the star is starting to go up the giant branch. So a bit brighter and cooler than it would have been on the main sequence. Again, somewhat eccentric and about a kiloparsec away. And then just analyzing the DR3 data, these were the only 2 black holes we found. But happily, there was a third one announced about 2 years ago now. This one's called Gaia BH3. This one has a long enough period, it's about 11-year period, that the orbit couldn't be constrained from the DR3 data alone. But in the process of preparing the Gaia DR4 data, the Gaia team discovered this object, and because it was sufficiently exciting, published it early. So the thing that's exciting about it is that it has a very high black hole mass up here of 33 solar masses. So it's the most massive black hole we know of in the Milky Way and immediate vicinity. And probably not unrelatedly, it's also a very metal-poor star of metallicity minus 2.5. That means it has something like 300 times fewer metals than the sun does. Here you can see the epoch astrometry and the epoch radial velocities. You can tell that this is a very well-measured orbit in astrometry just because the error bars on this plot are too small to see relative to the size of the orbit. The other exciting thing about Gaia BH3 is that it's in a stellar stream. So that means there are a bunch of other stars that have basically the same orbit through the Milky Way and the same chemical composition. And so we think the stream used to be a cluster, and Gaia BH3 was in that cluster. And so there was a nice recent paper by Daniel Marin-Pina, who's here, trying to model the evolution over there, trying to model the evolution of this cluster. So he did a bunch of models. You can see here's one that matches the observed number of stars and their distribution in 3D in the Milky Way pretty well. And then says, does this dynamical model, which has some binaries in it also, produce binaries like Gaia BH3? And so you can see here are the observed period, here are the periods, eccentricities, and mass ratios of dynamically formed binaries in the simulation. And then this dashed line is the observed properties of Gaia BH3. And indeed, they get some binaries that look similar to the observed one. And so in this model, the binaries that make it to the end have to be systems that form dynamically and have had several exchanges in the cluster, not binaries that formed as a primordial binary and just underwent normal binary evolution. Okay, so something I started to say earlier, the nice thing about these Gaia black holes is that we can measure the composition of the companion stars. So here I'm showing just a cutout of the spectrum of Gaia BH1, which is a solar metallicity star with a 9 solar mass black hole, and the same part of the spectrum for Gaia BH3, a low metallicity star. You can see these lines are much narrower because it's low metallicity. And so not only can we measure metallicity, but we can measure all kinds of other elements. And this is something we think we'll only ever be able to do for these kind of black holes. Right? In 20 years, right, we might have 1 million gravitational wave sources, but we'll never know what the progenitor composition of any one of them was. Whereas for these, actually irrespective of whether the binaries form as primordial binaries or whether they get mixed up in clusters, in either case, the composition of the companion star should be very similar to the composition of the progenitor of the black hole. So far from Gaia, we have only these 3 systems, 2 of them at about solar metallicity and black hole masses around 9 solar mass, and then 1 at minus 2.5 and 33 solar masses. So I'm a simple astronomer. You know what I'm going to do next. I'm going to fit a line. So there are reasons to think that some version of this relation might exist, although it should be somewhat more complicated. And that is that very metal-poor massive stars probably have weaker winds than stars of the same initial mass at solar metallicity. And so that means that a massive star can hold on to more of its mass as it goes through its post-main sequence evolution without blowing it away in winds. And so if you look at models for the progenitors of gravitational wave sources where we see higher mass black holes, most of them will predict that those massive black holes are forming from low metallicity stars. And so at least it's now the case that the most massive black hole we know also has the most metal-poor progenitor. And so it seems like it's some support of that model. But of course, it'd be good to have some more data points on this plot. And I'll come back to that in a few minutes, because there are some other black holes where we have these measurements. Okay, one thing I want to say about this system, since it's the most massive black hole, is a natural thing to ask is it actually one black hole, or could it be two black holes in a close binary? Something like this. And this is a model that we can actually test with precision radial velocities. And so this is some work by my student Pranav Nagarajan. So what he's done here is simulated the three-body motion of a star like this that's orbiting two black holes in a close binary, and then fit it with a Keplerian orbit. And you can see it looks pretty good on this scale, but once you zoom into the residuals, you get a lot of structure. And that's just because a star orbiting two black holes feels a different gravitational potential than a star orbiting one. And so in these residuals, you have both a high-frequency term, that's basically this rotating dipole gravitational potential of the inner binary, and you see structure on half of its period. And then you also see a longer-term residual, and that's because an inner binary will make the outer orbit precess, so it's not closed. So if we make precision radial velocity measurements, we can test whether we see these kind of residuals. And so that's what Pranav did using the espresso spectrograph at the VLT and KPF at Keck. And you can see up here is the radial velocity curve. Here are the residuals, and then we just zoom in to increasingly higher precision. And the end story is that even at the precision of a few meters per second, we don't see any evidence for non-Keplerian motion in the residuals. So we can measure the mass function very precisely, but it always looks like a closed two-body orbit. And then we can do simulations and say what kind of inner binary orbit could accommodate such a good fit with a two-body orbit. And so these different curves show basically the predicted reduced chi-squared for our observations if you had an inner binary with different mass ratios, orientations, and inner periods. And the observed orbit lets us rule out any inner binary with a period of more than 1.5 days. So we can't rule out an inner binary with a period less than 1.5 days because that's so tight that its gravitational potential would look basically like a single black hole. On the other hand, a binary that tight would merge in less than a Hubble time from gravitational waves, and so it would have to be very fine-tuned that it's already too tight to observe but hasn't yet merged. And so on this basis, we think this system, Gaia BH1, is definitely a single black hole. We'd like to make these kind of measurements for the other systems and more systems that we find in DR4 because it is predicted that there should be some stars orbiting two black holes. And basically this kind of measurement, I think, is the only hope we ever have of detecting a binary black hole in the Milky Way. Okay, so here's now a population census of the Milky Way's black holes. On the x-axis, we have orbital period, which scales with distance, or with separation. On the y-axis, we have distance. So up here, we've got all the X-ray binaries. Down here, we have these black holes from Gaia. And then in between, there are a couple non-accreting black holes that have been discovered through radial velocity surveys, some of them in clusters. And so you can see, although we only and there's also this one black hole out here, actually, that is isolated and was detected by microlensing. So if you look at the y-axis, you'll see that all three of these Gaia black holes are closer to Earth than any of the X-ray binaries. And we think that Earth is not in a special place in the galaxy. So that makes us think that these systems are intrinsically more common than these. They're just harder to find right now. That is, if you took these systems and moved them a little bit farther away, we wouldn't be able to resolve their orbits with astrometry. But if you took these and brought them closer, you would still see a bright X-ray source. So although these are underrepresented in the observed sample until December, they seem to be tracing an intrinsically more common population. Okay, that was the black holes. We can also try to find neutron stars with Gaia. We do a similar selection, but focus on objects with a bit lower masses. And there are now 21 published systems where we have pretty good radial velocity follow-up over most of the period. The radial velocities confirm the Gaia orbit, and we measure precise enough masses that we think the companion is probably a neutron star. Here's a little movie showing their orbits. So here are the yellow stars trace what Gaia is seeing, the luminous star. Each one of the red measurements is an astrometric scan projected in 2D. And then the cyan point, which we can't see, is what we think the companion is doing based on Kepler's laws. And so you can see, just looking at these, we have a range of periods, shorter periods up here going to longer periods between about 100 and 1,000 days. You see most of these orbits are not circular, but are ellipses. That's because they're eccentric. And then you can see that the ellipses traced out by the luminous star are usually bigger than those traced out by the companion. That tells us the companion is more massive. These systems are difficult to form in a similar way to the Gaia black holes, in that, again, you have to fit a progenitor star that wants to get large inside a small orbit. And they're additionally difficult to form because we think the progenitors of neutron stars usually, or the neutron stars themselves rather, usually get a kick when they're formed. But these orbits are pretty wide, so you can't accommodate a kick of more than something like 100 kilometers a second. And yet they're there. Another thing that's odd about these systems is if we look at just the metal poor ones, they all have weird spectra. In particular, they're all enhanced in lithium. So here I'm plotting in red the spectra of the metal poor companions to neutron stars, and then in black I have a comparison spectrum of a normal star with the same metallicity and composition of other elements, and you can see they always have a lot less lithium. Quantify that in this plot here, where this is showing the absolute lithium abundance as a function of temperature. There's some structure in this because the survival of lithium in the photosphere depends on temperatures. But you can see all of these neutron star candidates are in the tails of this distribution. And so we actually don't really understand where this lithium is coming from. But the reason I'm showing it is that we think it tells us that there's definitely something chemically odd about these stars. And that tells us that they must have formed together with their companions. There must have been some kind of interaction of some kind. Right, you can't explain this if the neutron star forms first and then only gets paired up in a cluster later on. Okay, I said we'd like to measure the mass distribution. Here's the observed mass distribution. So we have two black holes around 9 solar mass, one at 33, that's way over here. Then a bunch of neutron star candidates, all at around 1.3 to 2 solar masses. And so I asked before, is there a gap when we looked at the X-ray binaries and the gravitational wave sources? Well, we are sensitive to dark companions in this mass range. That is, if there were a 5 solar mass black hole orbited by a solar type star, it would be easier to find that astrometrically than it is to find these neutron star companions, where the companion is only 1 to 2 solar masses. But we haven't found any 5 solar mass black holes. So we can at least say that if these low mass black holes exist, they're much rarer than the neutron stars. We can infer something similar from the gravitational wave data. Of course, we just don't have enough objects here to say whether this is just a valley in the mass distribution or if it's a valley, how deep it is. We can also probe some structure in the neutron star mass distribution. So you can see we have used between 1.3 and 1.9 solar masses. This one was massive enough that it got its own name. These measurements have, again, a precision of a few percent, so they're pretty good. And what's different about these mass measurements compared to the other kinds of neutron star mass measurements we have, like those in recycled pulsars, is that here we're pretty sure these neutron stars have not accreted any material from their companion stars, because their companion stars are on the main sequence and have never evolved. And so we think we're measuring something like the birth distribution of neutron stars, at least the ones that survive in these kind of binaries. And we think we can use this to constrain some supernova models. Okay, just on the mass gap, here I now take all the known black holes and neutron stars in the galaxy that have good mass measurements. And I plot now as a function of orbital period. All the neutron stars down here, here are the Gaia ones, here are the ones in pulsars. You see the masses don't look that different. And then up here are all the black holes from different mass measurements. And so you can see this bimodal mass distribution exists in all of these populations. It still doesn't mean it exists in the underlying population, but in all the ones that make it into binaries where we can actually make a mass measurement, this population is bimodal. Okay, there was another exciting black hole discovered, or black hole candidate discovered just a few weeks ago that I wanted to highlight. This is now in another globular cluster, Omega Cen. But the discovery method is kind of similar to Gaia, but also somewhat different. So Omega Cen has been studied with HST for more than 20 years, mostly because we use the calibration source. But there's been a lot of careful work to make a catalog of proper motions and just epoch astrometry for these hundreds of thousands of stars in Omega Cen with that many epochs of HST data. And so there was this paper recently by Matthew Whitaker, who's a student at the University of Utah, involving some other people in this room, where he took these individual measurements for all the stars in Omega Cen and fit orbits to them. And there's at least one case where it looks like the companion is a black hole based on the epoch astrometry. So here now we have 2D astrometry measurements. You can see this color bar shows time. And you see clearly the star is not moving in a straight line. So you can then fit an orbit to it. When you fit that, you get a constraint on the mass of the unseen companion that has some degeneracy with a proper motion because you're not fitting the whole orbit, right? You only see about half of it. But even with that degeneracy, the companion mass is too high to be anything other than a black hole. And so the best fit mass here is something like 4.5 solar masses. I mentioned that partly because I want to come back to this question of how does a black hole mass depend on metallicity. So with just the Gaia black holes, it looked pretty good. There's also a bunch of X-ray binaries where we have a metallicity measurement. They don't change the story too much because they're almost all about solar metallicity. There's one that's probably significantly above 10 solar masses, Cygnus X1, but its mass is pretty uncertain. Then there's also 2 black holes in the globular cluster NGC 3201, discovered by radial velocity surveys. But we don't know their masses exactly because we only have lower limits in their mass because we don't know the inclination. So I plotted the lower limit here. But assuming random orientations, the true masses are probably within this error bar, right? They'd have to be very face-on for them to be much more massive. And then there's this object in Omega Cen at metallicity minus 1.8 or so, where the mass is only about 5 solar masses. And so maybe you won't be shocked to find that this line I drew earlier was a bit too good to be true. There's probably more to learn here. I will say that people that do cluster dynamics simulations tell me it's not necessarily unsurprising to find lower mass black holes in a cluster because their models predict that the most massive black holes will interact and most will get kicked out of the cluster. So by the time you observe, you only observe the low mass ones that are still there. Okay, so one of the things we've been working on recently is before Gaia DR4, can we find more black holes based on the DR3 summary statistics? This is work by Johanna Müller-Hohn, who's here somewhere, up there. So what Johanna has found is we can use a summary statistic in Gaia that's called Rouvet. It's basically a summary of the astrometric excess noise, and relate that to the size of the orbit, even in cases where we don't have a published orbit in DR3. And then similarly, we can take the RV uncertainty or the RV scatter and relate that to the total peak-to-peak RV curve, even in cases where we don't have an orbit from epoch radial velocities. And so using these together, you can use, if you take these together, you can use the observed astrometric scatter and the observed RV scatter. use them as observables and vary the properties of the binary, like the period and the companion mass, and fit for M2. And so this method works pretty well in finding Gaia BH2, which is unlike Gaia BH1, it has this epoch RV scatter. And applying this method to the catalog of observed red giants in DR3, she found a bunch more candidates for which the inferred mass suggests that there's a black hole. And so she's done some follow-up on these now, and they'll be among the first objects we look at in DR4. Another thing I wanted to mention, I asked at the beginning is, or I said at the beginning, one of the things we'd like to ask is what kinds of kicks are black holes born with? Gaia can help us here too, because Gaia can measure proper motions of black hole binaries, both X-ray binaries and Gaia black holes. And we can compare then the space motions of the black hole binary to the normal stars that are in the same part of the galaxy or have the same kind of orbits. And so this is some work, again, by my student Pranav Nagarajan, where we take some X-ray binaries, plot them in a tomb ray diagram. So this y-axis here is basically non-radial or non-azimuthal motion in the Milky Way. The y-axis is radial motion. And so a thin disk star should sit at the center of these semicircles. All these black stars are comparison stars. And then these actual black holes you see are like 3 sigma outliers. So that suggests that they got some kind of kick when they were born, or they're in a halo population. So there are at least some black holes where we think there's pretty strong evidence from their orbit through the galaxy that they were born with a kick. On the other hand, there are some black holes where it seems like they were born without much of a kick. So there are a couple of binaries where we have a massive star and a black hole in a detached orbit. One of them is this one, where we have a significant eccentricity. You could explain that if the orbit started circular and then became eccentric. Another one, this one, VFTS 243, the orbit is very circular, even though there hasn't been time to circularize it. And so we think, on the last slide I said there are some black holes that must have formed with a kick. There are also some that must have formed with very weak kicks. And there's actually more evidence, we think, for these weak kicks in a few black holes. The strongest evidence, I think, is this object B44 Cygni, this work that I did with Kevin Burge. So what's shown here is an X-ray image of B44 Cygni on the sky. And you can see there are these huge rings. It's like a bullseye pointing at B44 Cygni. These are X-ray light echoes from the last time B44 Cygni had an outburst. And then in the background, there's an optical image from, I think, pan-stars. So I can just look at this, zoom in again. And so one of these stars is B44 Cygni. I think it's this one. And you'll just notice that right next to it, there's another star. So that's been known for 30 or 40 years. But what Gaia told us is that that other star actually has the same proper motion and a consistent parallax with B44 Cygni. And the proper motion is measured precisely enough that there's a very low probability that this happens by chance. And so we then did some radial velocity follow-up and found even the radial velocity is the same. So the chances of this happening randomly is 1 in 10 to the 7. And so we think what's going on here is V44 Cygni, this X-ray binary, that's totally unresolved to Gaia. We have this mass transfer, the whole X-ray binary story, and something like 5,000 AU away, we have a bound tertiary star. That tells us a lot about the kick that the black hole was formed with, because the escape velocity of this tertiary is only like 2 kilometers a second. So if you give the black hole a kick that's more than 2 kilometers a second, you're going to lose the tertiary. And that means that this black hole at least must have formed with essentially no kick. And so we've done a bunch of simulations with different kick orientations and mass loss and things like that, and we find this one was born with a kick of less than 5 kilometers a second. So some black holes probably form by basically direct collapse. Okay, I'm going to skip through this in the interest of time. The last thing I want to say is that Gaia DR4 is coming very soon. Today, the Gaia collaboration released epoch astrometry for a set of 12 non-random sources on the sky that have exactly the data format and typical errors of sources in DR4. So if you're interested in astrometry, you can go download them. Here's one I downloaded and fit this morning. This is a system called Gaia 4b. So this is a a 10 Jupiter mass planet orbiting a nearby star. Very different astrophysically from the black holes, but in the astrometry, if you don't know the distance, it looks pretty similar. In DR4, we'll get twice the observing baseline, twice as many measurements, radial velocities for many of these sources. And so this will be useful for all kinds of binary star studies, but especially for looking for black holes. And so we've done a bunch of simulations. I won't get into the details because I want to end in the next minute or two. But the punchline is that we expect to find something like 30 black holes in DR4 just based on the observed population in DR3 and how much larger of a search volume we'll have in DR4. And in particular, we expect to find some massive stars orbiting black holes. So far we've only found low mass stars orbiting black holes, which are cool, but hard to explain from a binary evolution perspective. But here I've taken this population model of Norbert Langer, assigned black hole companions to O stars in the galaxy, whose positions and properties we know, according to that model, and then said, will they be detected in DR4 or not? And so you can see this model predicts that we should get something like 50 massive stars orbited by black holes in DR4. I am not saying we will get 50, but I'm saying that's what this model predicts. So if we don't find 50, we will be able to say something about this model. And just for context, here's the same plot in DR3. So in DR3, we wouldn't have been able to detect any of these. So the increase in search volume really is enormous if you just click back and forth between them. Okay, and the last thing I want to talk about is once we have a catalog of black holes, or really any kind of binary, we'd like to be able to use that to infer properties of the underlying population, but that's non-trivial because different kinds of astrometric signals are sensitive to different kinds of binaries. And so this is some work by Ben Pinnell, who's also here somewhere in the audience, that he's applied to binaries containing two luminous stars in the Milky Way, and showing basically where, at what part of parameter space you expect to be able to get full orbits, and at what part of parameter space you get partial orbits manifest in acceleration solutions. And applying this kind of machinery to observe catalogs of different kinds of binaries, you can infer the underlying period distribution or eccentricity distribution, which look different from the observed distribution. And so this is log period in days, yeah. And so we hope to do something like this in DR4 for the black holes, to turn our catalog of a discrete number of detections into an underlying model of the population. Okay. I'll just say very quickly. Also launching this year is the Roman mission. Roman is going to be able to find isolated black holes through microlensing. I won't go into a lot of detail about how, but if I give another talk in 5 years, I hope I'll be able to compare the properties of isolated black holes to those in binaries. And I'll end there.
Thank you, Kareem, for sharing at least a small fraction of the wonderful things you've done with us. There are questions. Let me first look for early career researchers, if there are any. Alex.
Yeah, great question. For BH1, no. For BH2, maybe. The star is more alpha enhanced than normal at its metallicity by something like a factor of 2. So it's possible that it's just a somewhat alpha enhanced star to begin with, but alpha elements are produced in supernovae. It's a little hard to get accretion to work, accretion of ejecta to work because the separation is so wide. So you expect, if you have like an isotropic ejection, something like 1/1 millionth of all the ejection will actually hit the star. But we've done some calculations. It's possible that more of the ejecta stays bound and then eventually accretes to the companion in a circumbinary disk or something like that. Yeah.
Good. Robert?
Similar question. Do you see any nucleosynthetic imprints of a common envelope evolution in the stars orbiting the Gaia black holes?
Yeah, so basically besides this alpha enhancement, we don't see any unusual elements. For common envelope, I guess it depends at what stage the common envelope happens, but I think on average, if you have a common envelope with a red supergiant, the material, first of all, you don't accrete that much during a common envelope, and what you accrete, I think, should have fairly similar abundances to the other star. So I'm not sure that we can disprove accretion during a common envelope, but I don't think we see direct evidence of it.
Yeah, thanks.
Thank you for the awesome talk. I had a question on the detectability of these black holes in the Gaia DR4, because you mentioned you need the spatial resolution for the astrometric monitoring. So how far out can you actually detect those black holes, and what fraction of the black holes you expect in the galaxy to be visible with DR4?
Yeah, good question. So it depends on how bright the star is. If the star is like a giant near the tip of the giant branch or a supergiant, then we can detect it, and it's in an orbit of order 5 years, we can detect it out all across the galaxy to like 15 kiloparsecs. But if it's a solar type star, then it's more like 2 kiloparsecs, because beyond that it gets faint, and so the uncertainties are larger. And so that means we expect massive stars, and especially red giants, to be overrepresented in the ones we find. So we think we understand the detectability pretty well. I think it's something like 0.1% of all the AU scale binaries in the Milky Way we can detect. So if we detect 50, then there should be 50,000. Yeah.
You pointed out this lithium anomaly in the neutron star systems. I mean, some of the black hole exobinaries also, I mean, V4 for Cygnus is a famous example. It's also lithium enhanced. Yeah. What about your 2 black holes? Do they show some lithium?
Yeah, the two, I think all 3 of the Gaia black holes have normal lithium abundances. Yeah. Yeah, I looked a lot at the papers about lithium. My assessment is basically that, people had various ideas, but nobody really solved the problem for the X-ray binaries, and then eventually people stopped working on it. So it might be good to look again. I think most of those models are hard to make work when the star is so far away from the neutron star. Right? The star is something like an AU, so it won't get much ejecta, it won't have as much spallation flux, but yeah.
I just want to add a comment on your mass determinations, right?
Yeah.
I mean, 2 of your black holes have this mass of around 9 solar masses.
Yeah.
And it's quite striking that if you look at the LIGO data, you get this strong peak also at the 9 solar masses. And
yep.
we think this has something to do with the internal structure. So that this is,
yep.
So we hope that you will find many more.
Thanks.
Good. I haven't forgotten you. Okay.
Okay. So we have 2 of them in DR3.
Mm-hmm.
This theoretical study says about 50 in DR. Factor, 4 in DR5 again, which would then be 2,000.
Yeah, so it's not quite as big of an increase, and the reason is that part of the limit in DR3 was that there were stricter cuts on which orbits are actually published, whereas in DR4 all the epoch astrometry is public, so we can fit it ourselves, and so part of the gain from DR3 to DR4 is that you have better data, but part of it is also you can search deeper in the data than we could when only the catalog was published. We have done simulations for DR5, and if we make the same physical assumptions, we'll get something like 200 in DR5, which is still pretty good. But of course, it depends on things we don't know very well, like what is the underlying period distribution and what kind of components do they have.
Hi, thank you for the awesome talk from my side as well. And I have a general question on the formation of the Gaia neutron stars, because you mentioned the kicks, which there is a way to make them work for the Gaia neutron star, but then it's quite difficult to explain the other neutron star in binary system that we observe. So what's your take home here?
Yeah, I mean, I'm pretty agnostic. I don't think there's a good model published that explains all of the properties very well. I mean, there's other evidence for populations of neutron stars that have low kicks. So if you look at both BE X-ray binaries, which has been some recent work, and at double neutron star binaries, there's kind of two populations in period eccentricity space. One of them with low eccentricities that requires a weak kick. And so there have been some different interpretation of that. But I think basically, right, it's that population that needs to make it in these kind of binaries.
Very good. One more question. 1 second.
Just another. There's all the time a kick from the supernova, or is that there are sometimes a supernova which makes a kick and one sometimes not? And then another question: what about if there would be all the time a kick? How could it be that there are these binaries survive at all? Is it more that these binaries is it pure that they are primordial binaries, or is it more that they are formed that they had first the supernova kick and afterwards they simply captured a binary with a later binary formation?
Yeah, thanks for the question. So, I mean, we can measure the kick to some extent, at least statistically. We can't measure the supernova at all, right? I mean, we have some observations of supernovae, and we can see, like, do the ejecta look symmetric or not? But I think in general, inferring the kick from supernova is very hard. So usually we can infer the kick, and then we can look at supernova models and predict, or see, do they predict a correlation between kick and properties of the explosion? I think the answer depends on whom you ask. I mean, I think most, I don't actually know the literature that well, but my understanding is there are models that predict supernovae, or things that look like supernova, both with strong kicks and with very weak kicks. And then there's also things that predict very weak transients, if any, with no kicks. And then the second part of your question, I think, so for the objects I talked about where we look at the space velocity, those are X-ray binaries, so they're very tight, and they had to have pretty large kicks. I think it's pretty secure that those didn't form dynamically, just because if your star well, in general, it's hard to capture another star. The only place it works very well is in a dense cluster, and even there it takes time. And so if you get launched at high velocity in the field, the probability of coming close enough to another star and having some kind of three-body interaction where you capture into a close orbit is very low. And even in a cluster, you don't have enough time if you just get kicked out. So I think the wide ones, where we infer lower kicks, maybe there's a chance of forming them dynamically, but not the fast ones.
Okay, yeah. Good. Let me actually now draw into the question before we thank Kareem a couple of logistical things. So first of all, I had mentioned Kareem had been a visitor every year. He's actually also this year here for another month, and often up on the hill, but since he's staying in Neuenheim, I imagine he might be willing to take a detour on the way up, so feel free to ping him about this. But more near term, there will be now, he'll be going out with students for drinks, and Johanna Müller-Horn, who is sitting there, will be organizing that. So if that's what you're interested, come down here and arrange it with them. And we will be having a dinner at 7 p.m. The current plan is at Salerno, 7 p.m. Brückenstraße here. Can I get a quick show of hands who might be interested in coming along, that I might adjust the, okay, 2, 4, 5, 6. Okay, good. Then I think 7, 8. Okay, good. Then let me do a slight upscaling of the reservation, and we'll see there. So Good. Thank you again, Kareem, for this wonderful talk, and let's thank him again.